Okay, I'm going to get started. So last time we were doing an introduction to emergence, and I want to just finish that by talking about emergence, not so much with physical systems, but with biological systems. So I'm going to make the bold claim that emergence is the central question of biology, and to prove it, I'm going to show you this quote, which is from Stephen Jay Gould. Nobody here probably knows who Stephen Jay Gould is, but he was a famous evolutionary biologist at Harvard University. And this date, 2001, February the 19th, so nearly 24 years ago. Anybody know what that date is special for? No? Okay, it's the date that the first draft of the human genome was unveiled. And so the first thing you do so what people did was they figured out how to sequence the genome, and they discovered that the first thing they did was they counted how many genes there are. And of course, you would expect that humans would have lots of genes because humans are the most complex organisms on the planet. And what they said was that humans, Homo sapiens, possesses between 30,000 and 40,000 genes. And this is Stephen Jay Gould writing about it. He wasn't involved in the project. And he said, our bodies develop under the directing influence of only half again as many genes as the tiny roundworm C. elegans. If you've heard about biology, you know that C. elegans is one of the organisms that people use to study. Now, actually what they did was this number, he thought the number was between 30 and 40,000 genes. And so that we had basically, C. elegans has about 20,000 genes. So we had maybe 50% to maybe twice as much more genes than this little worm that basically does nothing, okay? Actually, they faked the numbers, okay? Actually, the real number is that we have the same number of genes, okay? But anyway, what he realized was even if it's just 50% more or twice as much, what he said was this: the collapse of the doctrine of one gene for one protein, one direction of causal flow from basic codes, meaning the DNA, the genome, to the elaborate totality of the whole organism, marks the failure of reductionism for the complex system that we call biology. In other words, what people thought was, I've got a protein, there's a gene that codes for that protein. I've got another protein, there's another gene that codes for that. I've got some illness, alcoholism, autism, whatever. There's a gene that codes for that. Okay, that's what people thought. It sounds ludicrous, but that's what people thought. I'm simplifying a little bit, but directionally that is correct. And what you're saying is, well, that has to be completely wrong. It has to be completely wrong because we're obviously much more than 50% more complicated than a worm. And the key to complexity is not more genes, but more combinations and interactions generated by fewer units of code, meaning that it's not in the genes, it's how the genes interact. And many of these interactions, as emergent properties, is using the word emergent, the title of this course, must be explained at the level of their appearance, for they cannot be predicted from the separate underlying parts alone. In other words, if you want to understand something, a biological phenotype, you can look for the genes, and you'll find that, roughly speaking, anything you're interested in, you can ask which genes matter for that. They all matter. They're all interacting, but in different ways, different regulatory ways, and so on. But they're all connected with that. And so it's not like there's a one-to-one map of causality that you're used to in classical physics. Classical physics, you throw the ball, you know why it's going up, you know why it comes down. That's not true in complex systems. It's not true when you have emergence. And so that's what he noticed. So now I want to talk about very quickly, why would a physicist study biology? Okay, I'm a theoretical physicist. I worked on condensed matter physics, statistical mechanics, field theory, all sorts of stuff like this. Okay, I basically hate biology. Okay, I have no interest in how many legs some creature has or why it has some particular mating habits or whatever. Okay, so why would I study biology? So Okay, so what is biology? It's messy, it's complicated. You need to know chemistry. I hate chemistry. Everything in biology has an exception. So that means that, you know, anytime you say, well, this is something that all things do, there'll be somebody who says, no, 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 I've got this creature here. I've been studying it for the last 40 years. And this thing doesn't do what you said. It does something else. There's always an exception. And there's a huge diversity of phenomena. What are the equations? There's not even any obvious equations. And where is the simplicity? Where is the beauty? This is not like saying, oh, well, you know, we can just write down the Dirac equation, which is the simplest linear equation you can write down, which is Lorentz invariant, blah, blah, blah. And then bang, we've just discovered everything that describes all you know, atomic physics and so on. Nothing like that at all. So the answer is very simple. Well, some physicists study biology because they can create new tools for biologists. Like, okay, fine, I can make a better microscope. Make a better microscope, I can see stuff that happens inside a cell. And in fact, that's really important. You know, when you look at a cell, it's about the same as the diffraction limit of light. So when you look at it through a microscope, you can see a kind of cell, it's kind of blobby, you can kind of see a little thing inside it, but basically it's very hard to see. You go and invent new techniques, such as super resolution microscopy. The idea that you can use certain microscopic techniques to look within a cell beyond the diffraction limits, so scales that diffraction would say you can't possibly look at those things, but physicists invented ways to solve that problem. And now we can look inside cells. Not only can we take pictures, we can look inside cells and see things happening in real time. We can literally see the processes of transcription, translation, all the things, these things happening like a movie right before our eyes. That was all enabled by very, very clever physics techniques, and some of the people who got, who got credit for inventing those techniques received a Nobel Prize about 10 years or so ago. There's another reason why physicists study biology. You can look at the design principles and say, well, if we can figure out how the brain works, maybe we can make AI, right? So that's called biomimetic. Try to copy what biology does. Biology basically solves problems by evolution. It's figured out ways to solve physics problems, problems in the real world, complex problems, using techniques that we don't necessarily know, wouldn't have invented, and so we want to copy it. But the one that I feel is the most interesting motivation, it's my personal motivation, is this. Using biology provides new questions for physicists. So living systems expand the scope of physics. When you signed up to study physics, people said, well, what is physics? They said, well, it's the study of the universe, okay, everything in it. Okay, well, living systems are in the universe. Why can't we study those? Why do you have to be a biologist to study living systems? Physicists study living systems in a very different way. Most biologists study living systems for the following reason. They're funded to do biomedical research, to make you better, figure out why you have a kidney disease or heart disease or whatever it might be. Physicists have a different kind of question they want to ask. We don't want to fix the system because, in some sense, from my point of view, fixing very advanced organisms like humans is very important, but it would be like saying, okay, I've got a laptop computer like the one over there on the desk in front of Chan, with that one on the desk, there's something wrong with it, fix it, okay? But here's the problem. You don't know anything about computers. You don't know anything about semiconductor electronics. You don't know anything about material science. We're just giving you a computer and saying, fix it without knowing how it works even, okay? That would be crazy. That would be crazy. So what do physicists want to study? Not all physicists, but me and people who I brainwash. Why does the phenomenon of life exist? How is it that you can get matter and you just get a bunch of atoms that are completely not living, and you start putting them together and suddenly you get stuff that lives, that does all the things that living things do, including evolve, okay? That's not obvious that you have to do it. You can build living stuff out of stuff that's not living. How? Why? Where does that come from? How does matter, which is inanimate, self-organize into hierarchical, replicating, and evolvable structures that metabolize? We don't know. We don't know how this happens. It's a phenomenon that exists in the natural world, and we don't have an explanation for it. How does life inexorably become more complex? Why is it that maybe you can get some molecules like RNA and DNA, they sit around, they replicate and so on. Well, why didn't they just stop that? Why isn't the world just knee deep in self-replicating RNA slime? Why do we have us? Why do we have elephants? And then here's another thing. How does life program itself to adapt to wildly changing environments? The most interesting thing about life is this. When you hit stuff, physical stuff, like this, it makes a noise. That noise is because it is responding to your force by vibrating. It is doing basically Hooke's law. That is essentially what all physical systems do. You're basically doing Hooke's law. You're looking at a vibrating object in some way, shape, or form. But living systems don't do that. When you try to perturb them, when you try to make them do something that you want them to do that's different than what they're doing, they actually change the way that they function. They actually change the Hamiltonian, if you like. They do this in a way that's not like just saying, well, we're pre-programmed to do this. Living systems can actually reprogram themselves. Look at what happened in COVID. COVID was a nasty virus, is a nasty virus. And as we started to have lockdowns, and then we started to have vaccines and so on, that virus has evolved. The flu virus evolved. Everything in living systems that we don't like cancer, like viruses, like bacterial infections, like weeds that go and kill your crops. All of these things, when you try to deal with them by inventing a vaccine or doing chemotherapy for the case of cancer, or putting down Roundup to stop weeds, or whatever it might be, every time you do that, those biological populations evolve and become resistant to it. And we don't have a solution to that. We don't know where that comes from, and we don't really know how to even write it down mathematically, and we don't know, if we don't understand where it comes from, how can we do control theory to figure out how to solve those problems? So that's one thing that living systems do. It means that it's a dynamical system that I don't know how to describe. It's not dynamical systems theory. It's not stochastic partial differential equations. It's not field theory. It's nothing that I know how to do. Okay, and I'd like to know how to do it. Okay, how do living systems work when the number of particles is not thermodynamically large? Everything you know in physics applies to systems which have Avogadro's number of particles. That's not true in cells. In cells, you might have thousands of some proteins, maybe tens or hundreds of other proteins. The copy numbers are very small. That means that everything in biology inside a cell fluctuates very strongly, because it's not like there's some average and there's small fluctuations around that. It means that actually everything is fluctuating incredibly strongly because the numbers of particles are small. Well, if everything is fluctuating so strongly, how come the cell can do its job day after day, month after month, year after year for a century? Okay, and then we eventually die. Okay, that's amazing. How do they function so well with all that noise? And then when we think about living systems, they're spatially extended. They occupy space. They're not in equilibrium because we're driven by. We have to bring in energy. They form patterns. They're heterogeneous. We don't really know how to even think about them. So that is really a great challenge to physics. And I'm not going to go and talk about those things anymore. I'm going to finish that. That's why we study biology. Let me say a little bit about what we're going to talk about later in this course. So I do want to add something about biology in this course. I have changed it this year. I want to show you that stochasticity can stabilize patterns in space and time. So we are going to talk about how patterns form. And we're going to talk about how fluctuations actually stabilize patterns rather than destabilize them. Very, very counterintuitive. We only discovered about 10 years or so ago. Okay, I'm going to show you that the stochasticity can arise from environmental fluctuations. Stochasticity can also arise just because you've got so many small numbers of particles in a biological system that there are strong fluctuations. So the things that I will talk a little bit about I'm going to talk about how we can use stochastic field theory to study a phenomenon of ordering inside every cell in your body. This is something that was discovered about 15 years ago. It's still one of the hottest topics in cell biology, which is liquid-liquid phase separation in cells, this topic of biomolecular condensates. So I'm going to explain how that works. So this is a newly discovered compartments within your cells, which are membraneless compartments. And so we're going to talk about how we can study that using stochastic field theory. We're going to talk about order, not just in space, which is what you normally think about, but order in time. We're going to talk about how populations undergo cycles, boom-bust cycles of populations. And we're going to see that there's something very remarkable about that, because this, again, is a pattern in time that actually is stabilized by fluctuations. In fact, it wouldn't exist if it were not for fluctuations. We'll talk about briefly about ecological spatial pattern formation. I'm going to show you that that is described by stochasticity. And then if you want me to, in the last lecture of the class, when I'll give a talk about a topic of great current interest, if you want me to, I can talk about the origin of hallucinations in the brain and how the visual cortex works using ideas in statistical mechanics. So all of the things that we're going to be doing when we look at these biophysics things in this course, we're going to be using statistical mechanics techniques that I will teach you in this class, which came from quantum mechanics, but we applied them to classical systems, and we can apply them to biology as well. Okay, so that's the learning objectives, and I'm going to skip ahead from those things, and I want to go on to some real stuff. So before we start to do a real lecture where I actually write down stuff and solve math problems, anybody have any questions about the scope of the class? Okay, all right. So here's what I propose to do. Since most of you have not been in my class before, I'm going to review for you something very simple, the Ising model, which is the simplest model of ordering in physics, and we're going to talk. I'm going to try to. I will cover some of the material that I do cover in my emergence and phase transitions course, but in this course, I'm going to cover it from a completely different perspective. So if you went to my emergence and phase transitions course, looking at you, then you're still going to learn something new, because I'm going to do things that I taught there, but in a completely different way. Okay, so we're going to talk about that. We're going to talk about what is long-range order and how it can occur, and I'm going to show you that it depends on the spatial dimension, and then we're going to talk about how we describe this using statistical mechanics. Okay, so let's start off then with a review of the Ising model. And I'm going to sometimes give you references to these notes in these notes, and the references I'm going to give you are of two sorts. If I give you a reference that is say RG, that reference means in my book section 2.5, my book on lectures on phase transitions and renormalization. So you have that book. It's on the class website, Canvas website. You can just download it for free. Okay, the book was made from lecture notes that I made. All the publisher did was put a cover on them and then put them on Amazon and charge you $50 or $70 for them. So anyway, so I'm distributing those notes to you for free. So that when I talk about RG, that is the book that I mean. So everything I'm going to show you now is there in that book. Okay, so what we're going to talk about is a simple model of magnets. And I'm going to show you how one can understand how we calculate the quantities tell you about order. And then the punchline is I want to have you understand that a spatial dimension matters. And if I have time today, we will talk a little bit about symmetry. In particular, discrete versus continuous symmetry. So this model is a model which has discrete symmetry, and we'll talk about what that is in just a second. But the systems that we're going to be most interested in this course are ones which have continuous symmetry. Those are the things that enable us to understand really sophisticated topics, including, say, the Higgs boson, for example. All right. So what is this? What is the Ising model? So this is how it works. So you write down a lattice. So there is a lattice. There are I equals 1 to n lattice points. And then on this lattice, we have spins. So SI are spins on the lattice. Those spins are meant to represent the magnetic dipole moments of electrons. And they should be quantum mechanical. But we're going to pretend that they're not quantum mechanical. We're going to pretend that they are classical. So these are spins on the lattice, and these are going to be classical. And what are their values? These spins can have the value plus or minus 1. So we're using units, which are something like Bohr magnetron units or something like that. So that's very simple. You've just got a lattice of spins, up, down, up, down, up, 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 down, down, down. That's how I can read off the configuration of the system. Okay, then what I want to do, we're doing statistical mechanics. So everything in this course is statistical mechanics. So in statistical mechanics, we need to calculate the partition function. I'm going to review that for you. So to work out the partition function, I first of all need to know the Hamiltonian. So the Hamiltonian of this Ising model is as follows. First of all, it has an external magnetic field, and I sum over the spins SI. So imagine now that I have here my spins. I have an external magnetic field pointing up, and then my spins are sort of like this. They're just on each of these vertices, and I can't really draw them properly, but something like that. So you can see the spins, you can see there's an external magnetic field. So when you have an external magnetic field pointing in this direction, how does the spin interact with it? Well, the spin wants to lower the interaction energy, and the way it does it is the spin will try to point in the same direction as the external magnetic field. So pointing in the same direction as the external magnetic field means that you lower the energy. So therefore, the energy contribution from that is this. This just says the spin at lattice site I points in the same direction, up or down, as the external field H. And if it does that, then that lowers the energy. Because if H and S have the same direction, then minus H times the S is a negative number, and so the energy has gone down. Okay, so that is what is called the paramagnetic interaction. And if you've taken a class on graduate statistical mechanics, you probably solved that model exactly, and you can work out the partition function exactly for this model. But we're not going to do that here. Now, what we're interested in this course are interactions. So there's a term, which, and I've already got the sign wrong. There's another term, which I'm going to write like this. And this term is a term which describes how spins interact. And you can see it's an interaction, because in order to work out the energy of that term, I need to know the direction of the spin I and the direction of the spin J. So this is an interaction between spins. To work out this energy, I need to know two things. It's not just one spin on its own. So this is an interaction. And what this IJ means, that means that the site I and the site J are nearest neighbors. And what this says is if they point in the same direction, so Si is plus, Sj is plus, two pluses make a plus, then they will lower the energy by an amount given by J. So they want to line up in the same direction. Suppose spin I is -1, it's pointing down. Well, then spin J will also want to point down, and then minus is equal to a plus, and then a plus, and with a minus sign in front of the -J, that will lower the energy of the system. So what this says is this simple term says that spins like to point in the same direction as their neighbor. And this term over here is an interaction term, and this term is called ferromagnetism. A ferromagnetic interaction. Why? Because if I've got a spin over here, and its neighbor wants to point in the same direction, so this spin points up. This spin's up, now this one's up. But the neighboring spin for this one, which way is it going to point? It's also going to point up. And then the one over here is going to point up as well, and so on and so forth. So you might imagine that at very low temperatures, all the spins will be pointing up, or they could all equally well be pointing down. And so all the spins will point up, so the object will have a magnetic moment. And if it has a magnetic moment, it is magnetic. And if it's magnetic, it will stick to the door of your refrigerator. And that's what we want. Okay, this is the simple theory of what a magnet is. Okay. Okay, so that's the energy of the system. But we're not doing energy, we're not doing classical mechanics, and we're not doing quantum mechanics, we're doing statistical mechanics. So that means we have a system, we're in thermal equilibrium, and it is governed by thermal fluctuations. So we have to now look at how we describe it in statistical mechanics. So if I've got n spins, then I write down the partition function for n spins, and that is given by the Boltzmann distribution. So I take the trace of e to the minus beta times the Hamiltonian, and beta means 1 over Boltzmann's constant times t. There's some bug in this iPad, and so things get wiggly on the right-hand side, like it's Halloween or something like that. I don't know why. So I'll tell you what this trace means in a minute, but it's a trace over all the degrees of freedom. So I'll write it like that. And this is the partition function of the system. How many people have seen this formula before? Okay. How many people have not? Okay, you're the two undergraduates in the class? Master student. You're an undergraduate. So you've not taken a class in statistical mechanics or statistical physics or thermodynamics. Right, okay, yeah. It's not really about what I will explain what trace means in a second. But you've heard of the Boltzmann distribution. You've heard of the Boltzmann distribution. Okay, I will tell you what this trace means in a second. Okay, so what does this trace mean? What does this trace mean? It means sum over all the dynamical degrees of freedom. Okay, so that's roughly what it means, being very crude here. And the dynamical degrees of freedom here, these things are the spins, the SI. When I write down curly brackets, I mean the set of all the spins, SI. And so what this means is, when I sum over all the dynamical degrees of freedom, what it means is sum over every possible configuration of the system. So when I say trace, there's a reason I say trace, because in quantum statistical mechanics, it literally is the trace of a matrix. But what it means for classical statistical mechanics, in this particular case, it means sum over the value of spin 1. I can take two values, plus or minus 1. Sum over the values of S2. You can take two values, plus or minus 1. Sum over the values of S3, and so on, all the way to sum over all the values of spin n, which can be plus or minus 1. So that's what I mean by trace. So what it is here, it's like a big multidimensional integral, but it's a sum. So it's a big multidimensional sum over every single configuration of the system. So when you write down the Hamiltonian, that Hamiltonian, that's the energy, that is equal to, it depends on all the values of all the spins. So if I say to you, here's the configuration of all the spins, I just show you a snapshot like the one over here. That was really helpful, that was. What is the point of writing black on black? Okay, let's try again. Look over here on the left-hand panel. There I drew a configuration of spins. Every configuration of spins that you can write down has an energy associated with it. How do I know what that energy is? Well, I use that formula, this formula here on the left-hand side, and I plug in the values of the spins, I compute a number. That number is the energy of the system. So, when I do this sum, I'm making a sum over every possible configuration of the system, and I'm computing the exponential of e to the minus beta h. That's what Boltzmann taught us to do. Okay, so if you don't know about it, I will have to discuss it with you privately. I can't do it in the class right now. Okay, why do we care about the partition function? Well, the free energy of the system, the Helmholtz free energy, that's a variable that we'll call f, and it is related to the Hamiltonian by the following formula. Take the trace over all the spin values, or all the degrees of freedom, of e to the minus beta h. So what I'm doing is I sum over all the microscopic degrees of freedom, and that gives me the thermodynamic free energy. So this is a macroscopic description of the system, the thermodynamic, and over here, this is a microscopic description where you tell me about all the possible configurations of all the spins. And if I was doing another kind of system, I might be looking at a fluid. So I'd be summing over the positions and momenta of a system. But for this, we're talking about spin systems, and so that's what we are doing. Okay, so from the Helmholtz free energy, I can compute f over kbt, you can see then is minus the logarithm of the partition function. Okay. And when I say partition function, what is it a function of? So let's just look, let's go over that. So I've got a Hamiltonian, I've got this thing over here on the left-hand side. This thing over here. This is a Hamiltonian. It depends on these degrees of freedom, the S's. Those S's in this sum are like dummy variables. I'm doing a sum over all the values of these things. So at the end of the day, after I've done that, the quantity that I have on the left-hand side does not depend on any spins because I've summed over all the spins. So what does it depend on then? I'll get a number which is a sum of 2 to the n different terms, each of which is of the form e to the minus beta times an energy. So what will that thing depend on? It doesn't depend on the spins. Right? If I do this integral, what does I depend on? Which coefficient? Say? A. It depends on A. I do that, and I get something that depends on A. Because I've integrated this thing out. And then I've got whatever is left depends on A. So similarly, when I integrate out the spins, what do I have left? What does that depend on? So again, it depends definitely on n. Yep, so I've already got that written down here. Yep, what else does it depend on? H, yep, and what else does it depend on? It depends on temperature. Yep, I agree. Yep. What else does it depend on? Okay, you've done 2 of them now, so somebody else, you should do one. It's going to depend on how many variables I have, right? Okay, I've integrated out this n. The thing that is an exponential is given by this formula here. These things are just numbers, h and j. So when I do these calculations, I get this. What else will it depend on? It will depend on h, it will depend on n, it will depend on temperature. There's one other thing left. It can't be the spins, just like here. Okay, I've integrated, I've done a sum over the spins. So the only thing that's left is something that's not the variable that you've summed over. Okay, it's going to depend on j. Because to calculate the energy, I have to also know the value of j. So every term in the sum is going to involve j. So this is truly a function of all of these things. Yeah, go ahead. J represents, okay, J represents if this spin is pointing up, and you say if this spin is pointing up, then it will make this spin next to it point up. That is the strength of the interaction between the spins. Okay, and I didn't say, so I'm glad you asked about that. But always ask if I say something that you don't know what I'm saying or I forget, please ask. Okay, so J is called a coupling constant. It tells you about the strength of the interaction. And where does it come from? All these spins come from quantum mechanics. So I can write down the formula for J in terms of the interaction between the electron overlap, the electron wave function on this side, and the electron wave function on this side, taking into account Fermi statistics, the fact that they're fermions. So it tells you that imagine that the electrons in a crystal, if the electrons are far apart like this, they're not going to interact with much. If they're really close together, like 2 angstroms away from each other, their wave functions will overlap. and then they will have some interaction. So that's what J represents. It's a number that represents that. And so once I've done the sum over the spins, then the partition function will depend on J. Did I answer your question? Okay, great. Okay, so now what I want to show you is that from knowing F, we can get calculate a measure of order. Okay, so let's try to do that. Okay, so the first thing I want to show you is that so here's my claim. My claim is that any observable that I want to calculate can be obtained by differentiating the partition function. Okay, so that's my claim. So let me show you how. So what Boltzmann told us is the following: that if I have a configuration of some degrees of freedom, let's call them spins, and the probability of that configuration is probability of that configuration is equal to e to the minus beta times the Hamiltonian of that configuration divided by the partition function. So that's Boltzmann's distribution. So basically, you tell me what configuration you want. That's the configuration. That's the set of SIs, plus 1, minus 1, plus 1, minus 1, minus 1, minus 1, plus, etc. like that. And then to get that probability, I just take the e to the minus beta h and divide it by z, and that's a probability. And you can see how that is indeed a probability, because if I sum over all configurations of this P of SI, then that is equal to the sum over SI e to the minus beta h of SI divided by Z, but this is equal to Z itself over Z, and that is equal to 1. So the sum of these terms adds up to 1. So these are real probabilities. Okay, so that's what Boltzmann told us. So if that's the probability distribution, then that means suppose I have some variable which I can observe, let's call it O, which depends on all the spins. It might just be how many spins point up minus how many spins point down, or something like that. Any observable like that, then the expectation value of that variable is just written like this, and this is then the sum over all the spin configurations, the probability of the spin configuration times the operator, whatever that is, as a function of the spins. And that's what we call a thermal average. Okay, so now let's ask the following question. What is dF by dH? So let's see if we can just calculate that. So this is equal to d by dh And then I'm going to have minus kBt times the logarithm of e to the minus beta h. And minus beta h is beta times h sum over I si plus beta j sum over si sj. So that's the thing that we have. So this is equal to minus kBt, and then and actually I've got something wrong here. So that's right. Let's correct this. So it's the logarithm, and then I have the sum over the SIs. Okay, all right. So if I differentiate with respect to h, the only place that h occurs is right here in this inside this logarithm. So when I differentiate, I'm going to get one. I'm going to differentiate the logarithm of something. I'm going to get 1 over the thing. That thing is the partition function. So I'm going to get minus kBt times 1 over the partition function, because this thing in here is the partition function. And then when I differentiate with respect to h, that's going to give me e to the beta e to the beta h si. When I differentiate with respect to h, I'm just going to get beta si times h. So I'm going to get minus kBt, then the sum over I of si times beta, the sum of the spins from 1 to n, and then the partition function, e to the minus, or the Hamiltonian, e to the minus beta h, and then that's it. So then this derivative is going to be minus 1 over z, and then this thing over inside here, this thing is just the expectation value of the SIs. So it's minus 1 over kt. The kts cancel, and then I get the expectation value of the sum from I equals 1 to n of all the spins in the system. So if I differentiate the free energy with respect to h, and there's no z here, it's just a minus like that. So so that is equal to minus times the sum I equals 1 to n of si, and this object here is called the magnetization. And usually we talk about magnetization per spin. So the magnetization per spin would be m is 1 over n sum from I equals 1 to n, the expectation of si, and that is minus 1 over n d free energy by dh. So why do I care about this object? Suppose an equal number of spins point up as point down. Then if I add up all the spin values, half of them are pointing up and are +1, the other half are pointing down and are -1, so I get 0. So why do I care about this? So the magnetization measures the number of spins that are pointing up minus the number of spins that are pointing down, And then I've normalized by n, which is the total number of spins, which is the number of spins pointing up plus the number pointing down. So this thing is the fraction of spins pointing up. It might be a negative number, or they may all be pointing down, in which case it'll be -1. So this number, the magnetization per spin, is between -1 and +1. But the main thing is that I can calculate it by just differentiating the free energy. Okay, so everything we do in statistical mechanics, we never calculate because we don't like doing integrals. Okay, integrals are hard. Differentiation is easy. So what we do is we find something that we can calculate and then differentiate with respect to it in clever ways, and that enables us to compute anything that we want to do. Okay, so let me so tell you what we know. If you look at if you ask somebody how do we expect M to behave, so the answer might be like this. So what I'm going to plot over here on the vertical axis is M, and over here I'm going to plot the temperature. And let's suppose that there is no external magnetic field. So I've turned off the external magnetic field. So we're just looking now at the cooperative behavior of spins, the interactions, the collective behavior in them. So what you might say is, well, I know the answer to this, because if they all point in the same direction, I have a magnet. If I have a magnet, then the magnetization can be 1, or maybe the magnetization is -1. And if the magnetization is +1, then as I raise the temperature from t equals 0 to some finite value of temperature, what do I think is going to happen? Well, at 0 temperature, I can minimize the energy of the system by having all the spins point up or all the spins point down. Okay, if I raise the temperature, now what's going to happen is spins will start to fluctuate. So some spins will point up, but maybe a few will start to point down just by thermal fluctuations. Because remember, systems in thermal equilibrium do not minimize energy. They balance the energy with the entropy. So you might say, okay, fine, this magnetization is going to go down as I raise the temperature from absolute 0. Now, what's going to happen at infinite temperature? So let's suppose that J is some energy of interaction, a few joules or something like this. Now I raise the temperature to being, let's say, 10 to the 15 degrees. And let's suppose by some miracle the system doesn't melt. Okay, so what's going to happen? Well, all the spins are going to be fluctuating up and down like this, and the only thing that would stop them would be the energetic interactions between them. But the thermal fluctuations are occurring, are much more energetic than the interaction energy, the J, between the spins. So basically, as many spins will be pointing up as pointing down. So we would expect that somewhere out here at large values of J, large values of T, we would expect that the magnetization would be 0. So you might say, okay, well, let's just join up the dots. Maybe it just sort of goes something like this and eventually goes to 0. That could be one behavior, but it's not what actually happens. What actually happens, quite surprisingly perhaps, is that in fact, the magnetization goes down, and then at some special value Tc, it goes exactly to 0, and then after that, it's exactly 0. So this blue curve, this is what actually happens. And so this phase here is called the paramagnetic phase. This phase over here is the ferromagnetic phase. And it's characterized by the fact that we have order in this phase. There we have more spins pointing up than point down. So we have order. Here there is no order. So that's how we know the phase diagram of the system. Okay, so that's what we know, and it's exactly what you learned about on your mother's knee. If I take a magnet and I heat it up in the oven, or I hit it, lots of things like this, it will eventually stop being a magnet. It won't work. Then if I lower the temperature, it can then eventually become magnetized again. So this is what I've drawn you on the left-hand panel, is what we know happens, but now I'm going to show you that this is actually impossible. So now I want to talk about symmetry. So let me tell you the rough idea in words, and then I'll prove it to you with a few lines of algebra. So the basic idea is going to be this. So the basic idea is that for every configuration of the system, so let me call it, let's say S star. So that's a configuration. So this could be, for example, 1, -1, -1, 1, 1, blah, blah, blah. So something like that. So that's a configuration of all the spins. For every configuration of this of the spins, there is another configuration minus S star, which has equal probability. And that is true if H is equal to 0, if there's no external magnetic field. So the configuration I've drawn, there's another configuration, minus S star, which is -1, 1, 1, -1, -1, blah, blah, blah. That configuration has equal probability. And so when I do, when we compute the expectation value of M, which is 1 over n sum over all the spins, their average values, this is a bunch of terms with, and some of those terms are exactly, for every term in the sum, there is another term which is minus it. And so what that means is for every term, for every configuration in the SI, there is another configuration with all spins reversed. So when we sum over all of them, the terms all cancel out. And we get that M is equal to 0. And this is true. I never told you what the temperature is. This is always true. Do you have a question at the back? No? Okay. If you have a question, please ask. Okay. Okay. So we get M is equal to 0. So that says, and this is true for any temperature, And so what it tells us is that ferromagnetism is impossible. So magnets don't exist, okay? Which obviously is a pretty bad prediction, okay? First prediction we make in this class is that magnetism doesn't exist, and that prediction is obviously complete rubbish. So we better try to figure out how that works. Okay, so that's the basic idea. Any questions about the basic idea before I go and show you the mathematical proof? Okay, so let's now understand this in more detail. So the basic reason for this has to do with symmetry. So what symmetry could we possibly have? So let's talk about that. So we have our Hamiltonian, which looks like this. So that's our Hamiltonian. Let's ask ourselves, what transformations leave the Hamiltonian invariant? Okay, so I'm going to make a transformation, and you'll see what I mean by transformation. So you might say, okay, well, why don't we, well, we can see one straight away. So let's ask ourselves what happens when h is equal to 0. When h is equal to 0, so now I don't have this term over here. You can see that this term over here has the following property. It's a product of Si times Sj. So if I reverse Si, if I make Si for every spin go to minus Si, then the term J Si Sj goes to J times the sum over I and J minus Si times minus Sj, and 2 minuses equal a plus, and so it stays the same. So it doesn't change. So that's one symmetry, but now we have h not 0. So if I have h, so now let's turn on h. And we make this symmetry, s goes to minus s. What other transformation could we make that would make the Hamiltonian be invariant? Okay, so what? Anybody got any suggestions? Flip the magnetic field, right? We can flip the magnetic field. If we flip h to minus h, then what happens to the Hamiltonian? So that I've got my Hamiltonian, it depends on the spins, it depends on h, it depends on j. And if I do this, if I make the spins all go to minus, so every single spin is flipped to minus, and I also change h to minus h and keep j the same, then what's going to happen is over here on the left-hand side, this term over here, I get a factor of -1 from the SI, I get a factor of -1 from flipping the h. And so the two minuses cancel out. And so my Hamiltonian has stayed the same. So this combined transformation, h goes to -h, s goes to -s. That set of transformations for all the spins leaves a Hamiltonian invariant. So this is what's called a symmetry of the Hamiltonian. Okay, so now what happens to the partition function? Okay, so let's write down the partition function. So I got my Hamiltonian. It's up here. Trace over all the SIs equal plus or minus 1. I've got e to the minus beta times the Hamiltonian. And now that depends on h, j, and the spins. So what I'm going to do, we're going to keep j the same. We're going to keep t the same. We're going to keep n the same. But what I'm going to do is I'm going to change the sign of h, and I'm going to change the sign of the spins. So over here, I have a minus h that's in here. Then I have j, and then I have all the spins. And that's the problem. So that's what happens to the partition function when I do this transformation. So I just replace h by minus h. Now, let's have a look at what this transformation does, this part of the transformation. S goes to minus s. So here, we're summing over s is plus or minus 1. So s is a dummy variable. It's like having an integral. Integral dx, so it's like having the integral dx e to the minus a x squared from minus infinity to plus infinity. If I made the change of variable x equals y, sorry, well, let me say it a different way. Let me make the change of variable y equals minus x. What happens? So I get the same thing now, integral dy minus infinity to plus infinity e to the minus a y squared. And I get the same result as I had before with x. Right? Because it's just a dummy variable. So if I make this change of variables in this integral, if you don't believe me, do it yourself. The answer is going to be the same thing. It's going to be just stay root pi over a. Okay, so it doesn't matter because the function is even. It doesn't matter that I've changed the value of the variable. I've just made a change of variables, but I still get the same answer. So changing s isn't going to make a difference because I have the spins occurring in here and in here. So if I make the change of variable si goes to minus si, it doesn't change anything. So then what I'm going to get for my partition function is this thing is then going to equal the partition function actually let me just backtrack. So it won't change anything in the j term, but it will change something in this term. So how does h come in? H comes in the term minus h times si like this. So when I change the sign of the si's, that basically makes the H go to minus H will then go to plus H after I've made the change of variable. So then this thing is equal to Zn of J, T, and plus H. So making H go to minus H and then changing S to minus S in the partition function undoes the change of H. Okay, so Zn of J, T, and minus H is Zn of J, T, and plus H. So it is symmetrical. So it's a symmetric function. So then if I compute the free energy per spin, so that is minus kBt log of the partition function divided by n. Then what I have is that the free energy per spin, which depends on H and J and T, is the free energy of minus H, J, and T. So it's an even function. Okay, so now let's compute the magnetization. So the magnetization is M of H is equal to minus dF by dH. That's how I define the magnetization, 1 over n dF by dH. So I just put the n on the left-hand side. But the free energy is the same thing, is an even function of H. So it's the same thing as dF by dH of minus H. And that then is dF of minus H by d of minus H, like that. And then that is equal to minus n times m of minus H. So the magnetization as a function of H is minus the magnetization of minus H. And this is an exact result. So since we have the symmetry, we can now set the external magnetic field equal to 0. And so now what I have is that m of 0 is equal to minus m of 0. And that means that m of 0 must be equal to 0. So without an external magnetic field, it is impossible for the system to have any order. The magnetization is always 0, and ferromagnets don't exist. Okay, well, that's the end of the course because there's no order. Order doesn't exist, so that's the end of the course. Enjoy the rest of the quarter. Okay, so there's something wrong with this argument. Okay, it obviously can't be right. Okay, but what's wrong with it? Well, there's only one thing that can be. We're computing the magnetization. It's an expectation value with a probability distribution. The probability distribution is the Boltzmann distribution. Because of the Boltzmann distribution's properties, then we prove that the magnetization is equal to 0. So the only conclusion you can make is that the Boltzmann distribution is not the correct distribution. So in your introductory statistical mechanics course, or your thermodynamics course, You were told about the Boltzmann distribution and you have to believe it, right? Okay, I just proved to you that it can't be correct. Okay, so next time I will explain to you why it's wrong, but not today. Okay, so it's very subtle. It's very cool. So everything you've been taught is not quite correct, as they say in Russian, and we'll see how to make a more careful description that can explain to us how the system is ordered. Okay, so that's the end of today's lecture. So let me stop the recording.